Good morning and welcome to another fun-filled day of 307, one of the last days. I think there's only today and Monday in terms of actual lectures. So hopefully you guys are, I don't know, I'm guessing some of you are glad that this class is going to be over, but at the same time, if you're taking 308, it probably isn't going to matter too much because you just got still another month of this. I don't forget that your case studies are due next week. So please be, I hope you took my advice and got a head start on that, because to try to do it all in one weekend is going to make for a very poor weekend. But it is due Monday at midnight along with the final homework. And then the final exam is on Tuesday from noon to 3:45. It'll be just like the midterm. I'll post it on Blackboard when the window opens, and then when it closes, I'll be on Zoom during the majority of the time for the final, from noon to 3:45. And then you just have to turn it in by that 3:45 deadline. All right. So let's jump over. And we can, I don't know why I haven't done this before, but I think at the end of yesterday, we had been wrapping up our discussion on solid liquid systems involving solubility, solid liquid equilibrium, and saturated solutions. And we had kind of ended on the discussion of colligative properties, looking at manipulations in vapor pressure, boiling point, and melting point as a function of solute concentrations as measured by mole fraction of solute. And so the presence of a solute in a solution results in the effective vapor pressure of that liquid being lowered, as well as results in an increase in the boiling point and a decrease in the melting point of that solution. And so that was given by the three equations here. We worked a short example determining the molecular weight of a solute based off of a measured boiling point. And so what we're going to look at today is liquid equilibrium, discussion of ternary diagrams, ternary systems, which is probably, I'm going to try to make it a majority of the discussion is looking at those ternary systems and how to read ternary diagrams and use them to solve problems. And then touching base on adsorption, looking at recovery from like vapor systems. It's kind of like, it's a little solid, liquid, solid, vapor, equilibrium type systems, but we'll touch base on that to kind of wrap up chapter 6. So when we're looking at liquid equilibrium, a lot of how we approach these problems falls under the realm of, miscibility of our liquid phases. And so if we have two liquids, say water and acetone, and they can be considered miscible, then we should expect one phase to form, which is a mixture of our water and acetone components. But if we have two liquids that are immiscible, that tells us that there's a likelihood we're going to be looking at two liquid phases. With little or no mixing between components. The easiest, image of that is, oil and water. The oil rests on top of the water if we're looking at things in terms of vegetable oil. And there's not going to be a whole lot of water dissolved in the oil or oil dissolved in the water. However, we can also have systems that are partially miscible, or we can have two liquid phases that form, but each component dissolves to a small degree. In the second component. Let's say I have liquids A and B, and I mix them in a container such that I have an A phase and a B phase. However, the composition of A could be such that there is the presence of B in the A phase, and there is the presence of A in the B phase. And I'm just giving you kind of an example in terms of an idea of, what that could look like in terms of things that we can consider, partially miscible or not. If the x sub A was effectively 0 here, and x sub B is effectively 0 here, then we would be considering those immiscible substances. And so the solubility and miscibility of liquids within one another largely dictates the types of separations that can occur among these components. Primarily because let's say we have a system where we have liquids A and B coming into a system. And let's say we have A has a component or a product, I'll say, which is product P. But A has a very high boiling point, but B doesn't have a very high boiling point. And P has a very low vapor pressure, it doesn't boil. And so if the solubility of P and B is greater than the solubility of P and A, then if we mix this system and then allow it to achieve some sort of equilibrium, we might find a system that when we draw off those substances, we get the majority of our product in the B phase now over the A phase. And so we look at this as a form of extracting our product from the A phase by using a solvent or B. So this is an example of liquid-liquid extraction. And so then what we could look at is doing some sort of flash, raise the temperature of the system to separate the B from the product without too much of an energy input. And so there's a lot of ways in which liquid-liquid extraction and knowing information in terms of solubilities is important. And so looking at this relative ratio of solubility, solubilities, a lot of times we call this a partition coefficient, which we denote K because apparently we always have to use K for everything just to make it confusing. And so the partition coefficient tells us how that split would occur if we had a substance being distributed between two phases. And so if in this system that I had here, I would want to know the partition coefficient of P in the B phase over the A phase. And that would simply be the mass fraction of my product in species B over the mass fractions of my product in species A. So that gives me an information associated with the expected breakdown of my product in these two phases if I'm looking at it in an equilibrium sense. So let's look at an example in terms of thinking about how this could work. So if I had 200 cubic meters of acetone water mixture, which contains 10% acetone. And if this mixture is going to be mixed with approximately 400 cubic centimeters of chloroform, at 25 degrees Celsius, so the question is, what percentage of acetone is transferred from the water phase to the chloroform phase? At equilibrium. If we are going to assume water and chloroform are miscible, and the K value of acetone, chloroform over water, is 1.72, which equals the mass fraction of acetone in the chloroform phase over the mass fraction of acetone in the water phase. And the density of the acetone water mixture is about 0.974 grams per cubic centimeter. And the density of the chloroform is 1.489 grams per cubic centimeter. Now let's take a look. So what we're looking at. So I have 200 cubic centimeters, acetone and water, where the most fraction of acetone is 0.1, mass fraction of water therefore is 0.9, and then I have 400 cubic centimeters of chloroform. I'm going to put it in this process. I'm going to call it a mixer settler because that's what a lot of liquid extraction systems use. It's a system that mixes the two liquids really well together, and then it's sufficiently large enough that an equilibrium achieves on the outlet. And so then I have my water-rich phase and my chloroform phase. But I don't know what the mass fraction of my acetone is going to be. So I'm going to draw this up. M1, M2, M3, and M4. So if I have 200 cubic centimeters of my acetone water phase, and my density was about 0.974 grams per cubic centimeter, that tells me that incoming feed is about 195 grams, my acetone water mixture. Also, for my chloroform, I had 400 cubic centimeters, and its density was about 1.489 grams per cubic centimeter, and so that mass is 596. And so from this, I know my acetone in is 195 grams times 0.1, because it's 10 weight percent, or 19.5 grams. My water in is 195 times 0.9, which is 175.5. So I know that I have 175 water because it's immiscible coming out here, and the 596 grams of acetone, or excuse me, chloroform, coming out in those phases because we said that they were immiscible. And so in order to find the mass fractions of my acetone in each of these phases, I have to use that partition coefficient. So it's the mass fraction of acetone in the chloroform over the mass fraction of acetone in the water phase, which was 1.72, I said. Well, the mass fraction of acetone in the chloroform phase is the mass of acetone in the chloroform phase over the total mass, or the mass of acetone plus the chloroform mass, which is 596 grams. the mass fraction of acetone in the water phase is the mass of acetone in the water phase, or 19.5 grams minus the mass above divided by the total mass, which is 19.5 grams minus the mass of acetone plus the mass of the water, 175.5 grams. So writing it this way gives me one equation, one unknown. Does everyone see how I did this, or do you want me to break it out further? All right, so if I look at that one equation, one unknown, and if I solve that mass, which is the mass of acetone in the chloroform phase, ends up being 16.8 grams, which means the mass of acetone in the water phase is 19.5 minus 16.8, or 2.7 grams. So if I'm looking for the percentage of acetone transferred to the chloroform phase, then I'm simply looking at 16.8 grams over the 19.5 grams times 100, which is approximately 86.1%. So that's how looking at liquid extraction with systems that are immiscible can be done. The partition coefficient is what is commonly used to look at the breakdown of a component between these two immiscible phases. So then the question becomes, how does liquid-liquid extraction work? With partially miscible substances. Well, this is where ternary phase diagrams come into play. They call them triangle phase diagrams. I just call them ternary phase diagrams. And what a ternary phase diagram allows you to do is, one, determine the presence of two liquid phases, and two, estimate the composition of the liquid phases that form. And so let's look at a ternary phase diagram together and discuss it. So hopefully you'll see my PowerPoint presentation now. And you'll see this ternary phase diagram between acetone, MIBK, and water. Okay, this needs to go away. And you'll see, I wonder if it'll let me draw. Oh, cool, it will. So we have acetone, water, and MIBK. This apex here is pure acid. Oh, this is like really thick. Hold on. Pens. Thinner. So this is pure acetone. This is pure MIBK. And this vertex here is pure water. And everything within the triangle phase or ternary phase diagram is some mixture of these three components. And you'll note here, there's a 95, and that corresponds to a mole fraction of acetone of 0.95, where 95% acetone falls on this line. 50% acetone in this mixture falls on this line. And looking at water, you're going to be looking at the lines here. This is the 75% water per mole fraction line. This is the 50% water per mole fraction, and then MIBK is on this line. And it might help if I color code it. You might hate it. So this is for acetone. Just get really colorful today. How's that? This can be for water. And then like this can be for MIBK. So you kind of get an idea of which lines to use for which component. And then you'll notice this kind of umbrella here, this envelope. So this envelope denotes the area where we have the presence of two liquid phases. And so if I like to say mix acetone water and MIBK, not C, such that I went to plot that as one mixture, and the mixture fell somewhere in this area. Let's say my mix ended up here. That mixture at equilibrium would split into two phases. So if this was my mix point, I would have two liquid phases form. And the way I determine the composition of those two phases is I follow this line here. And this is what's known as a tie line. It tells me where my liquid phases are going to form, or it's going to tie those two liquid phases together. So I would follow the line to the edge of this envelope. And this would tell me where my liquid phases would be. This would be liquid phase 1. And I know this is getting messy. Liquid phase 2. And so let's start practicing with this. I'm going to erase this in about 10 seconds, but hopefully this quick rundown of the ternary diagram gives you an idea of how it works and how it can be used. One other thing to note is that in this region A, that's going to be the region where one liquid phase is going to form. All right, so I'm going to clean this up. And we can look at doing some examples together. Okay. So let's say I'm going to mix 15 grams of acetone with 20 grams of water and 30 grams of MIBK. And I asked, what are the compositions molar of liquid phases or phase when these three are combined? Well, I need to know the molecular weight. Molecular weight of acetone is about 58.1 grams per mole. Molecular weight of water, 18 grams per mole. MIBK is 100.2 grams per mole. So I've got 15 grams of acetone. So 15 divided by 58.1 tells me how many moles of acetone I have. Or 0.258 moles. Molecular weight of water is 18. So 20 grams over 18 grams per mole tells me I have 1.11 moles of water. And then last but not least, my MIBK, I had 30 grams over 100.2 grams per mole. Which is 0.3 moles MIBK. So if I put all these substances together, I would have about 1.67 moles total. So then I could find the mole fractions of each of these substances. So for acetone, it would be 0.258 over 1.67. Or about 0.15 for water, 1.11 over 1.67. About 0.66. And for MIBK, hopefully it's the rest. If not, we're in trouble. I get about 0.18. That comes out to be 0.99, close to 1 with rounding. So I've got my mole fractions of each of these substances. So now let's see if we can put this on our ternary diagram. And so I had, what did I have? 0.15 or 15 mole percent acetone, 66 mole percent water, and 18 mole percent MIBK. So I had 15 for acetone, 66 for water, which is going to be somewhere right here. And what did I have for MIBK? 18. Which should be about here. So this would be my mixing point. And if that's my mixing point, then my two phases are going to be along a tie line that I can kind of make pretty close to these. So my first phase is going to be here. My second phase is going to be here. So this is going to be phase 1. And this is going to be phase 2. And so the composition of phase 1 is going to be approximately, let's see, MIBK for phase 1 is going to be what, 0.725. For acetone, I've got what, 0.225. And for water, I've got about 0.5. For phase 2, my MIBK is really low. About 0.3%, maybe. Water is going to be the most in this phase. And it's going to be like 82.5. And then the acetone will be the rest. Around 14, 15 mole percent, right? And so I've got an MIBK phase here and then a water phase here, where the acetone is going to be split between these two phases. Is there anything that I can further explain to clarify how this ternary diagram can be used? I would expect to see one of these on your final, primarily because it's a really good skill to have, being able to read these and use them to get these components and solve material balance problems involving liquid-liquid equilibrium. So let's look at another example involving ternary diagrams. So actually, I'm going to switch it back to the other share screen. So this is the example from the presentation that I had prepared. We have 1,000 kilograms of a 30 weight percent solution of acetone and water is to be mixed with a pure stream of MIBK. The combined mixture is going to be fed into a settler unit, which allows the two liquid phases to form and be separated. The question says, how much MIBK must be fed to the process to reduce the acetone in the water-rich phase to 5 weight percent? So let's take a look at this example together. So I've got a mixer and I've got a settler. I have 1,000 kilograms per hour of 70 weight percent water, 30 weight percent acetone, which means I just have 700 kilograms per hour water, 300 kilograms per hour acetone. And I don't know how much MIBK I have. So this is going to be M2 and it's MIBK. I do know I'm going to have two phases, an MIBK rich phase that forms and a water rich phase that forms. And I know for my water-rich phase, I want 5 weight percent for that phase. If only I could spell. And the acetone in this phase is 0.05. So I will be right back. I want you guys to think about this. How are we going to start this process? I'll give you a quick minute. I'll be right back. All right. So what's the plan? How can we take a look at this problem? Well, I have this piece of information, right? 5 weight percent acetone. So let's jump to this ternary diagram. Oops, I need to delete that. Let me clean this up. So I know for that second phase, my acetone concentration should be 5 weight percent, right? Which is this line. That tells me for that second liquid phase, I should be right here. So that's the phase that I want to form. So for this ternary system, in only specifying the mass fraction of the acetone, I actually specified the mass fraction of both phases. Because if I want that phase to form, by the tie line, I also have to have a phase on the other side of the tie line form, or one here. Does that make sense? And so the composition I'm looking for in terms of MIBK has to fall somewhere on that tie line. And the only way to get that 5 weight percent acetone, oh, excuse me, that's mole percent. Let me double check the problem, how I wrote it. Oh, I made it harder. Now this is in, let me see, is this in weight percent or in mole percent? So this is actually it's actually in weight percent. Or at least for the sake of this problem, we're gonna say it's in weight percent. I'll send an email after class to confirm whether it is or not. So those are the phases that have to form for the substance. Does that make sense? And so this is going to be the mass fractions that form out of my system. And so for this liquid phase, which I'm going to call this one liquid phase 1. Oh, I don't like the thickness of that pen. Make it thinner. If my acetone composition is 0.05, then my water composition is about 0.925. And my MIBK is only about 2.5%. For my liquid phase 2 that forms, my MIBK, because it's going to be an MIBK rich phase, is going to be approximately, about 86% MIBK. Then it's going to be approximately 10% acetone and 4% water. So with just that specification, I can find the breakdown of those two phases. And so I can go back to my system and fill this in. So for here, my water was what, 0.925. For my MIBK is 0.025. For my MIBK phase, I had 0.86, 0.1, and 0.04. So all I need to look at for this problem is an overall balance. So I can solve for this problem without having to consider that stream in between. Because what I have, if I'm going to call this M2, and this is going to be, let's say, I'm just going to skip the one in the middle, M3 and M4. I can look on at balances involving the overall system, so overall balances. And if I look at the water, I have water in equals water out. And my water only comes in on that first stream, or 700 kilograms per hour. Has to equal the mass fraction in the water phase, or 0.925, times M4, plus the mass fraction in the MIBK phase, which was what, 0.04, times M3. And then if I look at my acetone, same thing, acetone in equals acetone out, or 300 kilograms per hour, times the mass fractions in the water phase and the MIBK phase as a function of the M3 and M4 flow streams. So I have 0.05 and 0.1. And so what I'm left with is two equations, two unknowns. So if I solve for these three equations, I can solve for M3 and M4. M3 ends up being about 2,667, M4 somewhere on the order of 667 kilograms. And so with that in mind, I can then do a balance on MIBK to figure out how much MIBK I need going into my mixer. Or M2 equals the mass fraction, which is 0.86, 2,667 kilograms per hour. These are flows plus 0.025 of 667 kilograms per hour. Which I get 2,460 kilograms per hour. Now, I do want to emphasize that with this diagram, these diagrams, you know, it's still looking at graphical interpretation. So they're not going to be the best in terms of reading from. I'm not going to expect like, you know, perfect accuracy. Your answers are going to vary primarily because every time I do this, I have to turn the pen on. Being able to pick the point and read it properly, it's not going to be perfect. I would recommend though on the final, I will probably give you a ternary diagram. Just label them like I was doing here, so I kind of have an idea of what you're doing, so I can at least ensure when I grade that you're looking at the right areas and you're picking the right points. Even if your numbers are off a little bit, I'm still going to award full credit so long as you can demonstrate to me that you're interpreting the diagram properly. I want to go back though, primarily because we did this example. This was assuming that the diagram was in molar compositions. It's actually in mass compositions. So I want to update that example now that I'm reading it properly. So this is 65 grams total. It's actually a lot faster to look at it just in mass fractions. So looking at these in terms of weight percents, the acetone's 23 weight percent or 0.23. The water is 31. And the MIBK is 46. So with these mass fractions in mind for that example, if I go back to the diagram, I had 23% acetone, 31% water, and 46% MIBK. So let's see, 23% acetone somewhere here, 31% water is going to be about here, which is right around 46%. So it would be somewhere on the order here. Probably right here. So then those phases would be here and here. So this would be phase 1, and this would be phase 2. And you would read those compositions from that. I just want to go ahead and make that correction. A lot of times ternary diagrams are in weight percent. On a rare occasion, they're in mole percent. I just assumed that this was in mole percent incorrectly. So I apologize for that error, but hopefully that kind of clears it up. One last thing, we're really not gonna do a whole lot on absorption, primarily because a lot of it's empirical and the models are a little complex. But touching base on absorption, it's essentially a method where a liquid or vapor material adheres to solid material as a form of separation. And the degree of extraction or absorption is, like I said, largely determined with empirical models. And so you're going to be relying on a lot of like graphical interpretation or data provided to get an idea in terms of the breakdowns associated between the solid components and the components being absorbed onto these surfaces. I had a couple examples here looking at absorption of various things. I believe one of them's in your book. The second one, I'll go ahead and I'll make a note to post the solution on Blackboard, and I'll send an email when I do. To be honest, I'm not gonna require this in terms of information for the final. It's good practice in terms of looking at material balances for a different type of process, but in my opinion, there are a lot of other more important concepts and skills that I would have liked to see you develop in this course. So you'll see it on this last homework. Like I said, these examples are there, and I will give you solutions. But in terms of studying for the final, I won't put it on the final. I'll just tell you that, like, solid absorption, these types of systems will not be on the final. So that's all I have for today. I think next Monday we'll do a quick rundown in terms of what to prepare for the final, some kind of greatest hits, and I'll take some questions, and I'll have a couple of examples in terms of the type of problems you should expect to see for the final exam. But any last minute things? Thank you all for attending class today. I know it's not easy for many of you, and hopefully the recordings I've been doing have been helpful even for those of you that are here, so that you can kind of refer to it as you study and as you do homeworks. I appreciate all your efforts in the class and that you've been working with me. And for those of you that did the bonus quiz and provided me feedback, I did want to thank you all. I will take all that into consideration in terms of ways to improve this course and adjust my interactions with students and my delivery of this content. I know the online format probably isn't the best way to do this class, but with today's current climate, this is the the most effective way that we can do in terms of developing instruction while maintaining the safety of you all as students, as well as myself as the faculty instructor. So don't hesitate to reach out. I will be looking at email this weekend for case study stuff. My only request is that try to ask as specific of a question as possible. I'm more likely to respond than, I don't know what to start on the distillation column. You're not going to get a good answer out of me, but if you're saying, how can I apply the recovery values into the problem? That's a more specific question, and it's easier to answer than, I don't know how to get started on this problem. That, to me, that my answer would probably be like, we'll draw it out, see what happens. So that's my only request. And thank you all, guys. Have a great day and have a wonderful weekend.